So we're live now. Hello, everyone. Welcome to our first session of 2017. Happy New Year. Actually, I guess everyone is relaxed and pumped up for the new year ahead of us. Today, we have a very special guest, Mr. Reza Rahman. He's the legend of Java community. He's written a very good book in Java Enterprise Bean 3.0, right? Am I right?
That's right, yes.
Yes. So how are you doing, Mr. Rahman?
I'm doing well, thank you.
Okay, so I think, how was your vacation? I think you just told me some days ago you were in a vacation. Is it good?
Yeah, a little bit of a break, not so bad. Just spending some time with the family. Pretty much a staycation.
So before starting the session, I'd like to let the audience know that you are listening via YouTube Live, and there is a section for the commenting on top of top right corner. I think you will be able to comment, and if you have any question, just comment there, and we'll try to cover end of this session. So that's all. We can start now. But before starting the topic, I would like to ask you about JUG in general. How we can participate in the various JUGs and how JUGs actually works in general. Can you tell us to our audience a little bit about it?
Yes. So the JUGs were started a long time ago by Sun, I think in the early 90s or even mid 90s. They're basically a way for Java developers at the local level to teach each other and get organized and get more involved. So that was the original goal of it. How do you obviously I'm very glad to see a South Asian JUG in JUGs, and especially active JUGs in South Asia, believe it or not, are very few and far between, which is surprising because South Asia is such a major development hub, and yet there's not that much actual training and grassroots level communities like JUGs in South Asia. So it's very good to see that you're attempting this. It's also good to see sort of the open mindset of trying to do this virtually rather than do this physically, and bringing in a mix of local speakers and international speakers. So all of those are right steps. I think right now what you need to work on is increase your visibility as a JUG worldwide. Maybe try to attract some more international speakers. Maybe do some networking via the conferences that you may have in your region of the world.
Definitely, we started with you. That's a great thing that we have you. We really want to thank you for that.
Oh, sure, no problem. My pleasure.
So let's start with the topic. So that can we start the topic?
Yes. So I'm going to switch to slides.
Okay.
Now. That's where most of the talk is going to be.
Right.
But do feel free to ask questions as we go along. And so first thing I'll ask you is whether you can actually see my screen now.
Yeah, we can see your screen, I think. Okay,
great. All right. So this talk is a little bit belated. So basically, as you can see, the title is relatively self-explanatory. I'll be spending most of my time actually talking about the features in Java SE8. I'll also talk a bit about what is on the horizon in Java SE9, which actually is solidifying rather quickly. So that has a delivery schedule sometime later this year or early next year. So that a lot of those features are getting pretty, I think, visible at this stage. And maybe if there's time and there's Q&A, I'll briefly talk about what you can expect beyond Java SE9.
Right.
So briefly, in terms of introductions, my name is Reza Rahman. I'm an architect. I'm a consultant with a company called CapTech Consulting. It's a US national company. But I also have a life outside of work as well. So I've been active in the community for a very long time. I'd say about 15 years or so. I was a Java evangelist with Oracle as well, amongst other things. I do lead the Philadelphia JUG today. Okay. A little bit about my company. I believe in it. There's several values that you see in this slide that correspond with the things that we do in real life. And of course, our customers also appreciate us for those reasons. And there's all kinds of awards that our company gets all the time. Okay, so let's talk about Java SE8. Java SE 8 is the most significant release of Java SE for a little while. I think Java SE 7, Java SE 6, Java SE 5, these are all relatively minor releases as compared to the scope and the depth of changes that are in Java SE 8. It has seen relatively strong adoption so far. In the various adoption surveys that I've seen something as high as 70% adoption already, which honestly is very encouraging. Again, Java SE 8 upgrades usually don't happen that quickly because it's so foundational. The JVM is so foundational, people don't usually upgrade as quickly as they have and as quickly as they have adopted Java SE 8. And I do think it's worthwhile adopting. So there's a number of significant features, namely lambdas, streams, the datetime API, completable features, and a lot more. I will be talking about those features, largely focusing on these big ticket features, but I'll also talk about the minor features towards the end of the talk. Okay, so the first place to start, if you're going to start anywhere in a Java SE 8 talk, is lambdas. What are lambdas specifically? The long and short of it, if you were to create a tagline of it, the tagline would be that lambdas are the introduction of functional programming proper into Java, and that is without breaking Java, because essentially Java is an object-oriented language, and functional programming doesn't necessarily play very well in all circumstances with object orientation. So it was a very tricky balance to bring sort of functional programming paradigms into Java, and of course, there's good reasons to bring those in. People have been asking for that for quite a while. The basic reason for doing this is really to enable better declarative style programming. Java and by and large, all programming languages, higher order programming languages, are largely imperative languages. So we'll see what the distinction between those, between imperative and declarative is in a second. But basically, functional programming at a very high level allows you to do a bit more of declarative style programming, higher level programming, where you're telling the runtime what to do rather than how to do it. If you really want to take advantage of functional programming, the honest truth is that you do need a change in thinking. This is not merely just another feature, but rather a change in a way of thinking, which I'm not sure that most Java developers actually have done. We've seen lambdas now for about 2 years in the wild, and I have not actually seen a large-scale shift in thinking, either in the industry or in the developer community, in how they go about necessarily writing Java programs. However, even if you don't become a true believer of functional programming and sort of transition into a different realm, what is factual, though, is that lambdas do have practical benefits for most of us. Because at the end of the day, it's not that we as developers will change our own programs very much to think in functional terms. What we actually need to have happen is the library developers, the ecosystem developers, vendors to sort of do this shift on thinking and adopt lambdas into their libraries. And that's where we will actually get most of the practical benefits out of lambdas. And in fact, that has happened to some degree, not to a great degree, but to some degree. And actually, the best example is Java SE 8 itself. So the Java SE 8 team simply didn't say, hey, there's a nice feature called lambdas. Here's some functional features that you can build into your programs. They went a step further. They actually used lambdas themselves in Java SE 8. So two concrete examples of this is the Streams API as well as the completable feature API. So these are actually sort of examples, very good examples of how libraries can go about adopting lambdas to achieve more declarative style of programming. The very nice thing about lambdas is they are essentially forward compatible, meaning that if you have an existing program, say written in Java SE 7 or Java SE 6, and you upgrade to Java SE 8, well, you can incrementally use lambdas in that old code by some minor refactoring. And of course, it won't break your old programs either. That's the way lambdas were developed on purpose. Okay, so digging a bit deeper into lambdas, what are they? As I've said, they're essentially introducing functional programming in the Java language to try to move to more declarative style programming. One very simplistic way of thinking about lambdas, if you're not very familiar with them, is that they're really a more compact way of representing what we would have as anonymous inner classes. So anonymous inner classes are useful in certain cases, as we'll see. The syntax is verbose. And one simple way of thinking about lambdas is they allow you to write anonymous inner classes a bit simpler. And in fact, that is foundationally what a lambda is. It's really just an anonymous function. So you have to understand the difference between functions and methods. Methods are essentially behavior attached to a particular object, whereas functions are behavior not attached to a particular object. So anonymous inner classes, in most uses, that's exactly what they wind up doing. Okay, and we'll see that as we look at a concrete example. So let's start with a bit of code that probably shouldn't look too alien to most of us. This is a bit of imperative code. Imperative meaning that it's very close to really machine code. You're outlining an algorithm on a step-by-step fashion and telling the runtime, okay, these are the steps that you need to execute. What are we doing here? What we're doing here is essentially calculating the highest score given a list of students. Okay, so it's a for loop, 2 if conditionals, 2 assignment operations, relatively vanilla, sort of ordinary imperative code. Excuse me. Per se, there's really nothing wrong with this code, right? There's nothing foundationally incorrect about this code. It's readable. You can write it fairly easily as well. Give me 1 second, please. Excuse me. I'm trying to fight a cold while doing this.
It's all right.
But if a functional programmer looked at this code, what they would try to tell you is that you could improve upon the syntax of this code by making some of the parameters, like what year are we matching for, and what collective operation we are performing in a higher order fashion. So in order to understand this, we actually have to attempt to rewrite this and be a little bit more clever about this relatively simple imperative code. So let's try this. So here is another way of accomplishing exactly the same thing. But let's take a look at this code a little bit closely. Okay, so this is essentially achieving exactly what we had achieved before. So it is looking at 2011, and it's going over a set of students and figuring out who exactly what exactly the highest score was. But what is happening here is that we've basically written more reusable, higher order methods to a flavor of list. Okay, so let's say I still have a list of students, but it is somehow a more clever list that has several higher order functions attached to it, namely filter, map, and max. Okay, so these are essentially operations that are operating on the entire collection. So filter is saying, okay, so let me, I have a list. I'm going to filter this list down by some criteria. Map is basically transforming the list in some way. Right? So it's saying, okay, I have a list of one type. I'm going to apply some kind of transformation operation to convert from one list type to another list type. And max is relatively self-explanatory. Given a list, please find what the maximum value is, right? So you could rewrite the code that we had before and make it more declarative, so to say, right? So make use of these higher order functions as opposed to manually writing your own iterative code with for loops and if statements and the like, right? So you could do this. The problem with doing this, though, at this moment is that you won't actually gain very much in terms of code readability. The reason you won't is because of the fact that we're using essentially anonymous inner classes. So two different anonymous inner classes in this. One is a predicate outlining, okay, so what exactly is my filter criteria? My filter criteria is that graduation year should be 2011. And my mapper, that's yet another anonymous inner class that's basically saying, okay, I'm going to convert from a list of students to a list of scores. And the way I do that is simply I get the score for a student. So again, these are basically a parameterizing behavior, right? So there's a filter operation. Well, filter by what? Well, filter by this particular condition. We want to do a mapping, a transformation from one type of list to another. Okay, so how do I go about doing that? That's also behavior. So in fact, the predicate and mapper objects, like most anonymous inner classes, are actually functioning as functions, not methods. So there's no actual need to have a behavior attached to an object per se. These are just standalone sort of floating bits of functionality. So this is basically what Lambda is trying to help, is to have this sort of code and have the code be readable. And the best way to see this is by jumping into an example by transforming this code further and applying lambdas. So here it is. So as you can see, this is a dramatic reduction in the code volume and a dramatic increase in the readability. We'll take it into how this is and try to explore, begin to explore what the lambda syntax actually does for us. But let's just take a second to take stock of this code now. So again, same thing. We have some list, right? Some list subclass that has these filter, map, and max capabilities built into it. Again, we're doing the same type of operations as we were before, but it's now much more clearer because there's not as much code clutter. There's not as much imperative code and anonymous inner class syntax to look at that's in the way. So you can actually tell right by looking at this code, okay, what is this code actually trying to accomplish? It's trying to accomplish a filter, it's trying to accomplish a map, and it's trying to accomplish a max. So how are we then reducing the syntax of the anonymous inner class? Well, very simply speaking, what lambdas are attempting to do is taking the actual core behavior part of the code and boiling the syntax down to express just that. Right? So let's take a look at the first one, which is student s, this funny arrow sign, and then get grad year equal to 2011. So let's go back and take a look at the code before. So if you really take a close look at the predicate really has one method to implement, namely op. This op method takes a student s as argument and returns a Boolean back. And really it's just a one-liner in terms of what we're trying to express in terms of behavior, which is s.grad year equal to 2011. So the compiler can actually guess all of this because the filter method will take a predicate as an argument. So there's really no reason why you need to explicitly instantiate a new predicate. So the compiler can do that part for you. It can also figure out, okay, the predicate object or predicate interface in this case has only one method to implement. So there's no reason to have the developer have manually write this code either. This is also something that the compiler can infer. So really what is left is the s.grad year part. So in fact, that is precisely what's happening here. Right? So s.grad year equal 2011 is basically expressing the method body. And there's an implicit return type here because the compiler knows that the return type of this particular what we'll now call a functional interface is a type Boolean. And we also know that the operation takes a single argument of type student, right? So what we can do is more compactly express that by expressing on the left-hand side of the expression specifically what the parameters are to that particular functional interface. Okay, so op is actually a functional interface, and predicate is actually a functional interface because it just has one method to implement. Okay, and basically the left-hand side, another way of reading the lambda is the left-hand side is the parameters to that functional interface of type predicate. And basically the right-hand side is essentially a compact representation of the body, which the body is essentially a one-liner. Same thing with map, right? So if you take the mapper interface, this is also what's called a functional interface. It has a single method extract, takes a student as argument, so student S will become essentially the left-hand side of our lambda expression, whereas the body is simply s.getScore. So that's a simplistic explanation of what a lambda is. So it's really the parameters that you need, literally what your method parameters would be, and then the arrow symbol, which is essentially, think of it as a class definition, a compact way of representing the class definition, and then the right-hand side of the equation is, right-hand side of the expression is really the method body. Okay, often even omitting the return type, because the return statement is implicit. So I hope that explains to you precisely what lambdas are. So this is really the most simplistic syntax of lambdas that you saw. You can get into more advanced syntax, which I'll also show you in a second. Okay, so I mentioned functional interfaces. So essentially, the type of a lambda is always a functional interface. And believe it or not, we've had these functional interfaces, although we're naming it now. We're saying this is the thing. Lambdas are a functional interface and functional interfaces are a thing. The reality is that we've had these in the JDK for a long time. So things like runnable, comparator, action listener, these are all essentially functional interfaces. Functional interfaces are a very simplistic definition of them is basically they're interfaces where you need to implement just one method. And actually now with lambdas, in order to enable lambdas, the JDK team has actually added a bunch of other such functional interfaces, largely corresponding to, if you may think of it, the general types of operations that you might want to perform as a function. So take to a predicate, consumer, and supplier is a good example. Predicate you already saw, right? So predicate is an example of essentially taking one argument and returning a Boolean, okay, returning just one outcome. A consumer is something that takes an argument and returns void. It actually consumes what the value is. It is usually a terminal operation, which we'll see in a second. A supplier is something that doesn't take any argument, but produces something, produces an object. Right? So this is usually the source of a lambda expression. But again, essentially, the key thing to understand is that a lambda is always a functional interface. Okay, so here's an example. So if I wanted to create a predicate of type string, okay, so a predicate that takes a string as an argument and returns a Boolean, well, you can express that by saying s arrow sign s dot is empty. Okay, so any particular string, we're doing an is empty operation on that, and this is our is empty lambda. Okay, and we can assign that as an object. So lambdas themselves are also objects, implicit objects in Java 8. Here are some examples of what was added. So all of these are actually added in one convenient place called the Java util function package. So one, if you are a library writer, or if you really want to become a true believer of lambdas, a good way to start is by looking at precisely what is available in the Java util function package. And that'll give you an idea of when you would want to apply lambdas. So already told you what predicate, consumer, and the predicate and consumer function is basically apply a function. Okay, so perform a particular operation. Similarly, supplier, unary operator, binary operator, int consumer, to-int function, to binary function, and there's a set of these. So all of these are essentially built-in functional interfaces. As far as I've seen, there's actually no need to create new functional interfaces yourself. The Java util function package is actually quite comprehensive. So it's almost a matter of figuring out what these things do and figuring out use cases of where they may apply in your particular program or library. So that's it in terms of the very basics of lambdas. Okay, now let's move into a bit more into the world of streams. And in fact, the developer community seems to be just as excited about streams as they are about lambdas themselves. So what exactly are streams? If you look in the existing collections API, the way we have it, and remember the collections API is quite old. It was introduced in Java SE5. The collections API, the way they are basically have unit operations. These are data structures, classical data structures that have unit operations. So things like add, put, remove, get, and so on and so forth. They don't actually have a lot of operations today that apply on the collections as a whole. There's a few of them. So for example, a good example is arrays.sort. There's an arrays object in the JDK, and into the sort operation, you can give it a collection as an argument. And that's one example of where you can actually apply a bulk operator on the JDK collections. But by and large, the collections API is actually just unit operations. So essentially what streams are allowing you to do now is have more of these sorts of bulk operations. And the big example of this is with the stuff that we've already seen actually as examples. So these are things like filter, map, and reduce type operations. So some examples would be obviously sort again, reversing the value of a collection, doing max, min, group by, transformations, right? Those are all essentially operations that apply to the collection as a whole, rather than a particular element in the collection. So these are the types of functionalities that were added via the Streams API. So it's a new set of APIs actually, rather than simply a set of methods that were added to the collections API classes. Besides giving you these features, another reason the Streams API is important is because they can also, in certain circumstances, improve your program's performance, and we'll see that in a second. The two ways that streams do this is lazy processing and parallel processing, and we'll see why that is. The best way to explain this is actually via example. So here is the basic anatomy of a stream. Okay, so let's start here before we go anywhere else. So the basic anatomy of a stream is that a stream actually has three different parts. A source, something that creates a stream, zero or more intermediate operations. So this is the stuff that will actually act upon your collection in one way or the other. But these are intermediate operations in the fact that they do not cause a stream to terminate. Okay, so they essentially give you a substream back when you apply these operations. And basically, a transformation would be an example of this, transforming the stream from one type of stream to another. And then finally, you will have a single terminal operation, a thing that will actually terminate your stream altogether and return you back into sort of normal Java world from the stream world. So before we go any further, one other thing that you should notice is that these bulk operations, like the ones we actually showed before in our example, filter, map to int, and sum, these are in fact not just added to the collections classes directly themselves. Okay, so In reality, they're actually another system altogether called streams. And in order to convert from a collection to a stream, you always have to call dot stream, right? So that is your typical way of where you would use streams. You would take a collections API and call dot stream. However, though, this is not the only way. The collections are not the only way you can apply. You can have streams. So this is really the reason why streams are a separate API. You can actually create streams from anything that is a sequence of data. So you could have, for example, an input stream with a set of bytes and create a stream out of that, a Java SEH stream out of that, and apply some of these stream operations there as well. But the typical way is simply to call collections.stream, and that will bring you into the stream API world, and then you can apply these bulk operations. So the bulk operations that I'm applying are, again, the very same examples that I started with. So again, a filter. In this case, we're saying, okay, the buyer's city is Philadelphia. And we're going to do a transformation operation on it called map to int. And so we're essentially transforming from a collection of transactions to a collection of integers representing the price. And then we're going to find the maximum, and then we're going to sum up all those prices. So basically, we're saying, get me the sales of all of the city of Philadelphia. Ultimately, what this stream is trying to say. Now, one other thing that I would like you to notice is the exact syntax of these two lambda operations in particular. I told you before that the lambdas could be compacted even further. So these are actually two examples of how that can happen. So notice that in the left-hand side of the filter lambda, the lambda that is in the filter operator, we've omitted the type also. So it's not transaction T, it's simply T, right? And the reason we can do that is because, again, the compiler actually can infer that because you are operating on a stream of transactions, well, the type of T has to be transaction. Right, so you can omit that part as well, the transaction T part as well, and simply say T, and then express the rest of your method body. Similarly, in the map to int, we're using yet another variant. Right, so we can actually, if all we are doing is calling a simple method, like say get t.get price. So a full syntax of this written out would be transaction T, arrow symbol t.get price. Well, in both of those cases, all we're trying to do is call the get price method of a transaction. There's even a more compact way of representing that by saying colon. Okay, so that's an even more compact way of representing a lambda. Okay. Right. So that is it in terms of the basic syntax of what a stream operator does. And if you look into the Streams API, there's a number of these sorts of operations. Yes. Yeah.
I have a question, actually. I'd like to ask you a question about parallelism. I have seen a lot of blogs that says that it's performance degrading. Do you want to say something about that?
Yes. So that is the next sort of point of discussion.
Okay, sure.
So let's take a look at this stream for a second. So if we look at this stream, and if you were to do a very naive implementation of this, you would actually possibly iterate over the collection 3 times, right? So if you were to possibly write your own API to do this, you would probably iterate over the stream once to do the filter, and another time to do the transformation, the map to int, and yet another time to do the sum.
Right.
So in fact, this is, so if you say that, then if you wrote this code in an imperative fashion, you would get better performance, because you would only iterate over this collection once as opposed to 3 times. So the question then is, well, wouldn't this cause a performance problem? If you were to use streams, wouldn't it perform less than writing this code in an imperative style? Well, the answer to that question is that no. Actually, streams are implemented in a relatively clever fashion. Okay, so this iteration over the collection actually happens just once. The reason that is that the entire stream actually doesn't do anything until you call the terminal operation. So streams behave a lot like under the hood behave a lot like a compiler. So when you call these filter and map to int and all of and one or more intermediate operations, what actually happens under the hood is that the streams API creates an execution tree. It doesn't actually perform the actual execution. It simply creates an execution tree all the way down to the terminal operation. So only when the terminal operation is invoked is when each value in the stream is actually propagated down this essentially execution tree. Right? So you'll take, this won't be like, okay, when I call filter, it's going to go over my entire array and filter each. What's actually going to happen is that it's going to build out these operations, filter, map to int, and sum, and say, this is my execution chain. And when you call sum, it will actually take each element of the array and run it through the entire execution chain. So say do a filter. Okay, does it pass a filter? No, it doesn't. We'll stop there. Move to the next element. Well, the next element, does that pass the filter? Yes, it does. And then let's do a transformation on that. And finally pass it to the sum method, which will aggregate all the values one by one throughout the entire stream. So that is one way, one thing that that lambdas do in order to enhance performance. So although this may look like it's iterating over the collection multiple times, it actually doesn't. So this is one source of confusion for developers. They you might think, okay, using streams, is this going to degrade my performance? Well, no, it's not going to. The other way that streams enhance performance is by using something called a parallel stream. So in this .stream method, when you call .stream, it actually implements this execution tree in a single thread, in a sequential fashion. Right? So each element in the array is taken through the execution chain one at a time. If you call .parallel stream instead, what that does is that it actually makes the execution of the entire stream parallel. So if I call parallel stream in this case, what would happen is that the underlying JDK would actually break up my my collection up into parts and give each of those parts to a separate thread. And the thread would actually do execution of the filter and map to int separately on separate threads, and even do the sum on separate threads, and finally do a summation operation to reconcile all of the threads at some point in time. So what this gives you is better throughput. So you're able to go over, especially if you have very large collections. Let's say collection, and when I mean very large, I think we're talking about something in the order of, let's say, 1,000 or a few thousand elements. Then you will actually get a performance benefit by essentially using parallel stream and giving those thousands of bits of data to different threads altogether. And the way this thread mapping actually works is that JDK comes with a common thread pool. And the way that thread pool is configured is that it's configured to be equivalent to the number of cores that you have. So if you have, let's say, a 4-core CPU, well, you'll spawn 4 different threads to work on your stream. Now, while that sounds good, it actually is a bad thing if you apply it inappropriately. So if, let's say, you have a list, a collection that has 100 elements to it, and 100 elements, you're using a parallel stream to process 100 elements. Well, the problem with that is that you don't actually need parallelism in that case. Most implementations, most operations that you'll perform probably on 100 elements are going to be relatively quick. So introducing parallelism in that case will actually introduce more overhead. because you'll have to spawn threads. The workload will have to be distributed across these threads, and then all of those threads will ultimately need to be reduced and coordinated and the like. And there's obviously there's going to be some synchronization cost involved as well in doing all of this parallelization. So for small workloads, actually you will see a performance degradation for using parallel streams. So your best bet is to simply use dot stream in those cases. But if you have a sufficiently large data set, then it absolutely makes sense to use parallel streams instead. Okay, any other questions on streams or lambdas?
I have one question actually on this topic. Question is, we have used here map to int, right? So if we use instead of map to int, we just use map, would the compiler would able to understand we are trying to do a sum?
That's a good question. I think not. If you look in the signature first, the sum operation, I believe it only works on floating point or integer values. So a generic object, it wouldn't know how to do a sum on. So I think you won't even be able to do a sum unless you did a map to some kind of type that the compiler can infer to be working on the sum operator. Right, so there's some type safety built into it, I believe.
Okay. So you can go first.
Okay, right. So that is about it in terms of a high-level overview of lambdas and streams. The next API that we can move into is the datetime API. So what exactly is the datetime API? In the JDK, we've had the concept of temporal data types for a long time, datetime data types for a long time. So these are classes like date and calendar and date format and Gregorian calendar for a long while, actually. This has been in place since Java 1.1. These are some of the oldest APIs in the JDK. These classes are perfectly fine as long as you are not doing any kind of manipulation of dates. So, and if you are using a calendar, using a Gregorian calendar, these are not issues. The reason is all you really do in these sorts of program is either read the temporal data type or write it, right? So for just reading and writing and storing a temporal value, Java util date actually works just fine. Date format actually works just fine. But if you try to do any kind of manipulation, date manipulation, let's say adding to a date or subtracting from a date or trying to figure out the difference between two date values, then you actually have a real problem. The Java util date API just isn't designed for that type of thing. It's largely an sort of a simple data holder. And the type of code that you wind up with in doing that type of manipulation with the Gregorian calendar object really is quite scary if you ever done it. The other big problem is that prior to JDK 8, the only implementation of calendar that was available in the JDK was actually just Gregorian calendar, which is basically the Latin-based Western calendar. So if you had to write a program that needs to make use of any other date system or calendar system, let's say Hijra or Chinese calendar or any other type of calendar, well, you didn't have support for that in the JDK. So this is the two things that the datetime API really addresses. And in fact, before the datetime API, these problems were addressed by JODA-Time, which was essentially a library written by Stephen Colburn. So basically, those capabilities are now built into the datetime API. Essentially, the datetime API in JDK, it's really nothing much more than a port of JODA-Time, slightly modernized into the JDK. So very similar to JODA-Time, This is basically a fluent API. It makes heavy use of immutable objects in the builder pattern. It does have very nice features for manipulating temporal types, not simply storing and retrieving and displaying them. And it also has much better internationalization. So actually now JDK8 has calendar instances for all major calendar types in the world, including, as I said, the Chinese calendar, the Hijra calendar, and the like. So this is a relatively battle-tested API. Its Jura time has been around for a long time as well. It's been around for at least 10 years or more in production. So these are all proven classes and relatively proven APIs. The last thing to understand with the datetime API is that they interoperate with the older classes very nicely, as we'll see in a second. So there's a number of classes for the datetime API. Each of these classes actually is a much better object-oriented representation of temporal concepts. So you now have local time and local date, differentiating between the concept of a date and a time. There's obviously no such demarcation in JavaUtil date. The JavaUtil date represents essentially date and time. So now you also have local date time. Okay, so you have zone date time, which is a datetime object created for a particular zone. Similarly, zoned date and zone time, which I've omitted here. Clock is basically a representation of the system clock in milliseconds. Instant is similar to calling essentially milliseconds. Duration and period are representing lengths of time. Duration being a shorter shorter length of time. Let's say a few minutes or a few hours. Period being a longer period of time. Let's say a few years. Zone ID is helpful for creating zoned versions of datetime API classes. Similarly, there's month, year, day of week, and all kinds of other demarcations that are useful in manipulating these datetime objects and also expressing them in a more object-oriented fashion. A good way to look at this is by looking at an example. So let's say we wanted to create a local date time, and the way you do that is you simply call now. And these now operations are actually available in pretty much all of the datetime classes. You can create a current representation of whatever it is that you need to create, whether it's a local date time or a local time or a local date or what have you. You can, if you've ever tried to do a toString method on JavaUtil date, what you'll get is essentially gobbledygook. Right? It's an object-oriented representation of the memory space rather than a properly formatted date time. In utildate, if you want to get a properly formatted date, well, you have to run it through a date formatter. Well, you don't need to do that in the new datetime API classes. They all have default built-in formatters. So when you call toString, they basically will use that formatter to produce a much more readable string. And you can obviously change those formatters as well if you wanted to. Again, a couple of examples of datetime manipulation. Right? So if you wanted to add 5 hours, you can easily do that with the plus operator. And similarly for the minus operator, you can subtract 2 days, okay, from a local datetime and so on and so forth. Even more examples. You can call, you can create a specific instance of time, right? Local date in this case, and you can give it sort of sane values. You can create a period by doing a between operation between two datetime types. You can get years, months, whatever you want from a particular temporal representation. And again, you can do obviously manipulation types as well. Right? So these are literally 4 lines of code. Believe me, if you wanted to do this using the old classes, you would be probably looking at close to 100 lines of code or more to just accomplish the same bit of functionality. Okay. Any questions on date and time before I move on?
Particularly right now, actually.
Okay, moving forward.
Yeah, sure.
Completable features. Completable features are basically a better version of JavaUtil feature. JavaUtil feature was introduced in Java SE 6 This is a library that was created by Doug Lee. And in fact, completable feature is also a library created by Doug Lee as well. But it's a significant improvement over Java util feature, especially when it comes to so-called significantly more reactive code. Basically, as compared with Java util feature, completable features are non-blocking, they're event-driven, and they're composable and functional. These actually won't mean anything until we take a look at some examples. So let's try and do that. So let's take a look at this code for a second. This is the type of code that honestly I've written. I've spent a lot of my time in my career writing. So what does this code do? What this code does is that it takes a person and calculates, well, what can be the coverage, the insurance coverage for that particular person. And in order to do that, you have to go through a bunch of calculations. So you have to get the person's assets, their liabilities. Based on their assets and liabilities, you have to create a credit score for them. You have to get their all kinds of histories, but health history is one of the most important ones. You have to calculate their health score, and based on credit score and health score and various other things, you finally have to perform an underwriting operations to figure out, well, how much can this person be covered for in terms of their insurance. So this code looks relatively simple. The problem is this code can be very, very problematic. The reason for this is that each of these invocations, like get assets and get liabilities, and calculating credit scores, can actually be either CPU or IO intensive. Get assets in particular will typically involve getting data from remote systems. Same thing for health history, same thing for get liabilities. So these are potentially long-running operations. Calculating the credit score and calculating health score, these usually involve some pretty serious accounting calculations. So these are usually very CPU-intensive operations. So all in all, when you do all of these operations that are either CPU-intensive or IO-intensive all together in such a sequential fashion, this will become a bottleneck. So this system will essentially not perform very well because it will slow down whenever you are trying to calculate a person's underwriting. It will be essentially a throttle, a bandwidth throttle for the system. So how can you solve this? Well, you can solve this by essentially executing all of these distinct methods on separate threads, right? So you can execute a separate thread and return a Java util feature, just like I'm doing here, right? So you can do get assets on a separate thread and get a feature back, and do get liabilities and get a Java util feature back, and so on and so forth. So you can execute each of these things in parallel and try to reconcile the values by doing feature.get. So that's when you're going to get the actual value of your asynchronous process, the actual return calculation back. If you take a look at this code, though, it has one problem, namely that the get operation, the Java util feature.get operation, is actually a blocking operation. So although you can actually execute get assets and get liabilities and get health history independent of each other, you will actually wind up with a premature block because of the f1.get and f2.get calls. That will be essentially blocking calls, and the program won't proceed further, won't spawn more threads until both f1.get and f2.get are actually done. And the basic fundamental problem here is because of the fact that feature.get is a blocking operation, right? So you can try to reconstruct this code to avoid this, but in the end, you'll always wind up with something like this if you have multiple nested asynchronous executions. So Java util feature is actually very good if you're just doing one single execution of a thread, right? It's actually a very good semantic for that. It's the simplest possible way of executing that. But whenever you have these sorts of scenarios where you're executing multiple interdependent threads, you will wind up with essentially these sorts of scenarios where you have a premature block. You can solve this by applying callbacks instead. Okay, so you could rewrite this code using callbacks. I'll show you this code that I have on GitHub real quick. And I'll let you take a look at this code on your own time, if you will. So basically, I've rewritten that same exact code using essentially callbacks instead of features. Right. So what I do here is when I call executor.execute, which I'm spawning a new thread on, and I do get assets, well, I don't return a JavaUtil feature in there. Instead, what I do is I invoke the next operation, which is setting my assets value, okay, in an atomic reference, and counting down a countdown latch. So you can take a look at this code, but as you can see, this code is very, very complicated. And in fact, this is what is called callback hell. So you can have these sorts of asynchronous calls either in features or callbacks, but in both cases, you'll wind up with one problem or the other. The features are simple, but they will cause premature blocks, whereas the callbacks are going to be extremely complex. So this is the problem that completable feature is actually designed to solve. So basically, what completable features do is that they bring the syntactical simplicity of JavaUtil feature, and then they marry it with the non-blocking capabilities of callbacks. Okay, so let's see how that is. So let's imagine for a second that we've written this particular bit of code using completable features. So if you were to write this in future, the process payment method would return a type of feature, and the rest of this code will actually will look very, very similar. In fact, you have a feature.complete method. The big difference is that because it's feature, it will be a blocking call. Well, if you were to rewrite this like I have in completable features, this is how the code would look like. You would create a completable feature. So it's just an instantiation of a new completable feature. You would return that right away in your parallel thread. And in your separate executor, and in your separate thread, you're executing a separate thread where you're going to actually do the process payment. And when you get your confirmation status back, you simply call feature.complete. So this code is virtually identical, other than the fact that we're using completable features and futures. The difference comes in how the client code actually looks like. So in the client code, when you call process payment, we no longer get a JavaUtil feature back, and there is no get call. Instead, what we get is a completable feature which has a number of terminal operations built into it, similar to streams. And the one we are using in this case is called then accept. And then accept is actually not a blocking call at all. It is simply a callback registry. Okay. So what is happening here is that you're saying that when process payment finishes, then execute this particular callback, which is a callback is nothing much more than print out the value of the confirmation that I received. Okay. So this is essentially non-blocking as opposed to a blocking call. And it is still using simpler syntax. So now you can apply this syntax to our case as before. So let's take a look at this. Look at this code for a second. So in this case, each time I am spawning a new thread, I'm calling supply async of the completable feature object, and that is giving me back a completable feature back, and it is also executing the get assets method in parallel as well. Same thing for liabilities. And then in the calculate credit score step, I actually combine both of those operations. So you can actually combine and split completable features. So in this case, I'm doing a combine. And I'm saying, wait for both get assets and get liabilities to be done. And then when that is done, execute another asynchronous operation to do the calculating the credit score. And you'll get another completable feature back. And similar thing for calculate credit health score, and similar thing for the underwriting operation. Because there is no get call here, there is no premature block. So all of this is actually happening completely in parallel. The get assets and calculate credit score is actually being calculated in parallel like it should be. And there is only thread joins where we actually want join to occur. So either by doing a combine or by doing an explicit join to say, please bring this entire operation back to the current thread, okay, when it is done, and calculate the coverage for us. So as you can see, this is what completable feature gives you. They're non-blocking. They're functional. So all of these are using essentially functional interfaces. So you can use lambdas like this, and they're also composable. So when you have these sorts of scenarios, these sorts of complex scenarios of having multiple asynchronous calls that are interrelated, this actually comes in very handy. Okay, although it's not necessarily a very simple API to deal with. So there are some other features in Java SE 8 as well. I'm sort of out of time, so I'll briefly talk about all of these. These are some of them. You can take a look at them. So removal of permanent generation. So now there is no more permgen. Permgen and essentially heap is essentially the heap space. Some rarely used GC combinations were removed just to clean up the JDK a little bit more. There's something called an optional interface that was introduced. This also can be useful. Again, I think in practice it hasn't been used as much. And what this does is that it reduces the need to do null checks. Okay, because in case where something may return a null, it will return a wrapper and often a default object if you needed to. Default methods. So now you have the capability of adding methods and interfaces if you want to. This is actually something that was added in support of the Streams API. The JDK team itself needed to do this actually. Repeatable annotations. This is actually more useful for Java EE applications. So now you can have to actually repeat annotations on a given class or field. I talked about the fork join common pool. So now JDK actually has a built-in thread pool built into it. If you want to make use of that, you can. Parallel array sorting, similar to what you saw in terms of parallel streams. So now there's instead of arrays.sort, there's an arrays.parallel sort built into it as well. There's a standard encoding and decoding for base 64. This used to be essentially a Sun-specific class. So JDK 4.2 has some built-in capabilities. There are more compact profiles that were introduced in the JDK. So this is good for example, for IoT situations, as well as for server applications where you may not need things like Swing and AWT. There's a lot more. I'll tell you how you can learn more about those. So before I finish the talk, I do want to talk about Java SE 9 a little bit. I think in terms of feature sets, Java SE 9 doesn't have as many interesting features for developers per se, although there's going to be some interesting changes. So the biggest change is actually jigsaw and modularity. So this is actually introducing the concept of modularity into Java SE 9 itself. So you can dynamically add and remove components to your JDK. And similarly, there's actually a module system. So you could write your own modules as well that you could add and remove dynamically from your Java programs using Java modularity. So this is a big ticket feature for Java SE 9. Frankly, I'm not sure how much this will actually be useful, but we'll see. There's going to be a much better HTTP client, okay, HTTP 2 client, in fact, that was also WebSocket capable built into the JDK. Prior to this, there really wasn't any kind of this kind of support in the JDK. The most significant class was Java Net URL, which is really very poor, a very poor interface. And instead, you also have now the Jaxaris client API that is basically effectively an HTTP client. So you'll have the same type of capabilities built into the JDK now with the HTTP 2 client. G1, as of JavaSC 9, G1 will be the default garbage collector, which I think it will be actually a net improvement. There's going to be a Java REPL tool introduced in the JDK. Again, this has been a sort of long-standing request, especially from people trying to learn Java in the first place. I don't think most professionals really will have much use for a REPL, but it's useful for students that are just learning the Java syntax, and instead of doing Java C and Java, you can simply open up a shell and start typing some Java commands, and it will give you essentially output right away. Reactive streams is something else that is going to be introduced. Applets are going to be deprecated as of JavaSC 9, officially deprecated, and there's some other minor features as well in JavaSC 9. This is an evolving list. It will change a little bit here and there. So in summary, JavaSC 8 is the most significant release in years. It's been well received and well adopted. There's some important features like lambdas, streams, the datetime API, completable features that you saw in my talk. There's some other features that are coming in JavaSC 9. If you want to get involved in JavaSC 9, this is definitely the time to do that. So if you want to learn a bit more about any of this, I have some resources in my slide deck. And actually, my slide deck is available on my SlideShare account. I'll show you how to get to that in a second. But these are some resources that are in the slide deck. So these are, if you want to learn more about JavaSC 8, the official JavaSC tutorial actually has a fairly nice track for JavaSC 8. So that's a good place to start learning. If you want to get a complete set of features of what is in JDK 8, there's two different good resources for doing that. One is the what's new in JDK 8. This is also part of the JavaSC tutorials. And there's also, in the JDK project itself, there's a list of JEPs, Java Enhancement Process Requests, that you can dig into much more detail of what exactly each of the features are. And if you want to find out more about JDK 9, the best place to do that is in the OpenJDK sub-project called JDK 9. Okay, and that will give you all kinds of details about JDK 9. Let me show you how to get to this slide deck. It's quite simple. So you go to SlideShare, and I have a account on SlideShare. It's separated by my name, Reza_Rahman. And actually, this is the one of the newest talks I have. So this is the one with the 7,000 views here, and this is, if you click on this, this is the slide deck. There's actually a PDF version of this slides available. You can download it on SlideShare. If you wanted to, for example, give this talk yourself to a smaller set of folks, or in your company, or in a different jug, you can certainly do that. Okay, so that is it in terms of the slide portion. I know we don't have a lot of time, but certainly if there's any questions, I can address those.
Definitely. We have a few questions actually, not much actually. So
okay.
Can you go ahead?
Okay, Bulgur, should I start?
Sure.
Okay, okay, Reza. You said reactive streams in Java 9. So, I mean, some of us here is familiar with RX Java. So, is it that implementations from RX Java is be in Java 9, something like that? I mean,
no, so RX Java would be similar to completable features. I would say, with the completable features API, in most cases, you probably don't need RX Java. RX Java has even more complicated features than what completable features has. In my experience, to be honest with you, most developers don't even have the level of complexity needed even for completable feature, right? So an RX Java definitely would be a much more advanced. But basically, to answer your question, completable features, which is already in JDK 9, would be the equivalent of what you have in RX Java. Reactive streams are something a little bit different. Reactive streams is basically just a set of interfaces that you could potentially rewrite the NIO API, streams NIO API with in JDK. And it would allow for more control over readers and writers to control the flow of how much data they want to produce and consume. So it's a way of negotiating data exchange rates when you're dealing with streams. So that's what that is about. And quite honestly, that is quite an advanced feature as well. You only need that when you're dealing with very, very large streams of data.
I mean, okay. I'm familiar with something called break pressure in direct Java. It's okay. It's fine. Okay. Here we have a common question actually. I also get it from others sometimes that we all know that interface in Java is contained only method declaration and no implementation.
I am having trouble hearing you for some reason. Let me try to adjust my volume on my side. But could you repeat the question, please?
Yeah, sure. Okay. Now you can hear me?
Yes, much better.
Okay. We all know that interface in Java contain only method declaration and no implementation. And on the other side, when we need some method need to implement and other method need to, to the inheriting class to implement, we use abstract class. So what's the significance of using defender method in Java 8? I mean, in Java 8, there is a defender method.
Default methods.
Yeah, why people, sort of functionality same was present in abstract class. So people normally ask, what's the significance to introduce defender method or default implementation in interface?
Default implementations are useful for essentially for library writers, especially if you have an existing interface. Right?
Mm-hmm.
And many of the Java libraries do have existing interfaces, the JDK being the big example. And you want to add behavior to extend those libraries in one way or the other, then this becomes a very, very, very important feature. This is a capability that wasn't there before. So in fact, that was the real reason why it was introduced in JDK 8, is because the collections were essentially interface based. But at this point in time, especially to enable streams, they needed to add behavior to interfaces, and obviously that wasn't possible without introducing a change in the class itself. Now, in terms of when is it useful, abstract class versus interface, it would be useful, obviously, because Java is still a single inheritance system. So if you extend from an interface, you can only extend from a single class, right? You can't extend. Essentially, you're locked into that particular implementation. Whereas if you have if you implement the interfaces, you can actually change the behavior at runtime by simply mapping an object to a different interface. I don't know if that answers your question or not, but it's a subtle distinction. Most developers probably won't come across that.
Yeah, it is really nice to. Java is single in. Okay, and another question we got normally, actually, what is the optional feature in Java 8? Optional container object. It says that it's used to avoid null pointer type exception, but
what if it is
can you?
Mm-hmm. So let's say you have you're a library writer, and in some circumstances, your library can return a null value. The problem with returning a null value is that the consumer of your library needs to be aware that you're returning a null, and needs to do a null check to say, okay, I've made an invocation. It's is it null, and explicitly write an if statement to say, if this value is null, then do this. Or if you fail to do that, the worst case is that you'll get a null pointer exception. It's you'll get where you are not expecting a null, and the library returns a null. Well, you'll get a runtime exception if you didn't handle that. And the only way to handle that is by writing imperative else-if statements. What optional interfaces allow you to do is that as a library writer, instead of returning a null, you can essentially return an empty value. You can say, I'm returning something that's not going to cause you to have a null pointer exception, but be aware that I am returning an optional class for you. And that optional class actually has builder pattern APIs to declaratively handle the else if condition. Okay, so you can actually say optional and then get, and then you can get in that get value, you can say, am I getting an empty value or not, right? And you can programmatically handle that code in a more declarative functional style as opposed to having to write an else if condition. So that's really the big differential there. And you can also have callbacks, the same type of program model that we saw before. So you can say, okay, get an optional, and then if it's a proper value, do this, and if it's not a proper value, do that. And you can write that as in a one-liner in a builder API fashion, as opposed to having to write else if statements. That's a simplistic explanation of what the optional classes do. Again, I haven't seen a lot of usage for them because they are relatively more complex. It's just simply easier to not do a null check and get a null pointer exception, or to write an else if statement.
Okay, so let's take one more or two questions actually. Do you have any time?
No, Budur can go ahead.
Okay, so can we take more two questions? I think we already passed 15 minutes, so it's 11:46 here. So I think one question would be, is there any chance of a better abstraction of logging API in JVM? The common like SLF or J in future?
You can suggest it. I think the JDK team, this position is, they want to see. As such, if you do a feature-by-feature comparison, the util logging API is actually not functionally that different from anything else out there. So I think the JDK team, by and large, wants to see people adopt the current logging APIs before they did any significant enhancements to that. It seems like for some reason people are still using these third-party libraries for logging when the one that's built into the JDK functions actually just fine. For my projects in particular, whenever people are adding these third-party logging libraries, I always ask them, hey, why are you doing that? What is the benefit? When the JDK actually comes with just fine libraries. I think what needs to happen more is maybe more appenders, more third-party appenders for that build upon the Java util logging APIs. That's where I see the real gap. So whenever you're doing a file system based output or just console based output, it's virtually equivalent, the features that are in the JDK already.
Okay, so let's take the last question. Actually, we have a lot of students here who join our groups. So they have a common question like, I know Java Standard Edition quite, so how we can go forward? Like, do I need to learn Java EE or Spring Framework, or what? What should be the learning from Java SE to next step? So can you comment on that?
Yes. So the reality is that you can't actually, the real answer is that there's value to definitely in a professional setting. You need to know both Spring and Java EE quite well. And I know that's an uncomfortable situation, but the reality is that a lot of the Spring APIs actually depend upon Java EE APIs or build upon them in one way or the other. So the learning path that I would suggest is learning Java SE and then learning Java EE as at least some key APIs in Java EE, and then learning the Spring Framework. That I think is a good solid learning path for most professionals.
Okay, so thank you for with us in this session. Definitely, would like to have you in our future sessions if you have if you can manage time. Obviously, you are busy, I know. So
actually doing these virtual sessions is not very difficult. It's not very time consuming. So I already obviously I have my catalog of talks. You can always look at them on SlideShare. Your JUG members can decide whether any of those talks is of interest to them, and if it is, I'm happy to present this way, and also to try to find you more presenters that are willing to do virtual talks. I definitely think this is worth doing, and what you guys are doing is definitely worth trying, and looks like you've been successful so far. So I would continue on.
Okay, thank you, and thank you everyone, those who joined in this session. And this session will be available in our YouTube channel, and in fact in our group. So those who haven't seen will be able to see later. Thank you everyone. So that's all. I'm stopping the broadcast.
Okay, do give me a link to the. So yeah, let's end the broadcast. Thank you very much for everyone attending. Let's chat a little bit more and see how we can better expose your JUG to the world.
Okay.